All right, welcome to the video introduction to Project Zero. Okay, first of all, let's read imap.h. And by the way, you are not required to implement binarytree.h, only asoclist.h. All right, so we've got a pragma once. This is saying, basically pragma once means only include this file one time. The C++ preprocessor will otherwise include a file multiple times, and that will mess things up. All right, so the first method we have on our IMAP class, which is the interface, is the add method. That's going to add a key value pair to the association list. The next one is remove, which is going to remove a key and its associated value pair from the list. Then lookup, which is going to take a key and is going to return us the value. And then the size, which is just going to say how many keys are stored in the list. All right, and remember that because this is an abstract class, we're going to have to write an implementation of it. And that's what a soc list is. And that's why it's doing that subclassing of public IMAP KV. All right, and the template stuff, I'm going to refer you to the C++ guide to understand. So templates are a kind of parameterized type. We'll talk about them a little bit in class, but you'll have to figure it out a little bit on your own for Project Zero. All right, so what we're going to start with is links, because our linked list, we're going to implement our association list as a big linked list. Each of the links in that linked list is going to have a key with type K, a value with type V, and a pointer to the next link of type link. All right, so we're implementing sort of a linked list just like we would have done in CS 105, 6, and 7. And the way that we're going to create a link, so this is its constructor, so the constructor is always the same as the name of the class, is going to use this initialization list trick, so this initializer list trick. So this is the kind of a common way that you initialize member variables in C++. There's another way you might do it as well. You might just say inside of the constructor, k equals underscore k. But for a few different reasons, mostly style, we would prefer to use this initializer list when possible. There are some other reasons as well, some things relating to performance. Also, for example, if one of the member variables is const, then you can only initialize it using the initializer list. All right, so the initializer lists are a nice way to initialize things. Now then, inside of a soc list, note that this is inside the private part of the class, we've got count and root, which store the number of things in the list, and then also the root node. And then we've got a public default constructor. The default constructor is the thing that gets called no matter what happens when you build any of these association lists. You can specify multiple constructors, but typically you have a default constructor with no arguments. All right, so when I say the term default constructor, it means just a constructor that doesn't take any arguments. All right, and then note here that when we're using the syntax for zero, that actually means the null pointer. Sometimes in C, this is written as all uppercase null. You can do it that way in C++. I prefer to just use the number 0 instead. All right, and then moving down, we have the destructor as well. So the destructor gets called whenever an object is destroyed. And that's going to happen in C++ either when the object falls out of scope, so when it falls off the stack, if it's a local variable, so not if it's a pointer. The pointer falls out of scope, then you're just hosed. You've got a memory leak. But if you just have a local variable that's stored on the stack, if that falls out of scope, then the destructor is going to get called. So let's set ourselves up an association list type AL, and then let's do some operations. I'm going to leave you to figure these out. You can look at some of the test files in the tests folder. And then at the end of this block, so between curly braces denote a block in C++, the end of that block, that's where the destructor for AL is going to be called. And that's because AL is falling out of scope and it's a local variable. All right. Now, there's another way the destructor could be called too. So you could create a pointer to an assoc list, right? So I could do that by using the keyword new. All right, so let's create AL is going to be new assoc list. And that's going to call the default constructor. And I have to provide these template parameters, of course, too. Now, whenever I manually call delete on AL, then this destructor is going to run. And the job of the destructor is to kind of clean up all the things that the object is holding. So I encourage you to go through this code for the destructor and figure out how it's working. And you should also look at the lookup method. And a really big note here is that this destructor relies on your implementing remove correctly. So if you don't implement remove correctly, this destructor is not going to work. All right, and if you end up in any situations where your code is just kind of like, infinite looping for seemingly no reason and you can't really figure out what's going on, remember that this destructor is getting run. All right? Okay, so the next method is for adding a key and a value. So to do this, if the key and value isn't in the association list, you want to add a link to the association list. If it is in the association list, you don't want to add a link, and specifically you don't want to add a link to the front because that will change the size of the list, which we don't want to do. You just want to go through and set the right value. All right, then next we have this method remove, which takes a key and then removes that key from the list. And notably, remove is going to return true if the key did exist in the list, and it's going to return false if the key did not exist in the list. So for example, if you try to remove something that's not in the list, this remove method will return false. All right, now the next method is lookup, which takes a key and returns a pointer to a value. Remember, all these links store pointers to values. All right, and you should also ask yourself here, why is it important that these are const references? All right, what would happen if, for example, instead of using a const reference, we were to pass the key by value? All right, so think about this for a second. What would the difference be in terms of performance potentially? So you can pause the video now. But the answer is basically that if it were passed as a value, then what would be happening is that C++ would put that key on the stack, right? So for references under the hood in C++ get passed by pointer, and so they're very cheap. And it's important that it's a const reference because now we know that the reference won't be changed by the call to remove. All right, and of course passing things by value on the stack can be slow, especially when they're really big structures. Not when they're things like integers. It's fine to pass those as values. All right, and then note that the lookup method is already implemented. You should read through this method and figure out how it works. This is actually a really good litmus test for if you can kind of understand what's going on here. And if you're confused, draw what's happening as each of the pointers evolves, right? So in particular, as this node pointer evolves, draw some example linked list or association lists and go through and see what's happening and then see if you can figure out what's going on. And if you can't figure out what's going on, then this is a place where I really encourage you to work with a friend to go figure it out. All right, as long as you're not collaborating on code and just trying to figure out code that I already gave you, that's totally fine. And then the last method, this one should be pretty simple. I'll let you figure out how to write this one. So maybe do that one first. All right, well, that's pretty much it for P0. Good luck.